No, I'm not ready. I'm not ready. I'm clicking stuff. I'm getting stuff organized. Okay, I'm as ready as I'm ever going to be, which is not ready at all. I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today, because this is going out nationwide. No, globally. No, to the universe.
Said you are not prepared.
No. Just seeing that message from Peter reminded me, yes, Merry Christmas, Peter. I saw that video you sent me late last night. That was pretty cool. It made me laugh. So, hang on. Let me just figure out what is going on in my world right now. I really don't know. Where's the chat? Oh, there's the chat. Okay, I found the chat. Good morning to Chip, who was here at 12:44 a.m. getting an early start on being ready for the stream. Mitchell is here. We've got the audio up and running. Thanks, Mitchell. Stephen G can't make it today, but we have Stephen W as our replacement Steve, plus the little furry Steve. Sion is here. Austin, Imi, I think I saw earlier, some call it fun. Gavin and Delane, David, Luminator, David, another David is here. Sharky, Russell, Wagon Loads, Henrik. Henrik asked, do I like a hot dog? Yes, I eat hot dogs. Good morning, Peter, Dave, Paul Jones, Cable Tie, Nigel. G'day, Nigel. Hi to the UK. James made it. Now, I had a bit of an unfortunate thing happen yesterday. I don't know if you can see it through my glasses. You probably can't. It's probably not that easy to tell. But if I take the glasses off and you look on this side, particularly around here, you might be able to see. And you can probably see that this eye is slightly swollen shut. In sparring yesterday, I managed to eat a knee very, very quickly and very unexpectedly. It was a self-inflicted stupid thing. I was wanting to set up a takedown, so I did the classic jab cross hook and then shot for a double leg. But my opponent was a left-hander in a southpaw stance, which meant that his right leg was forward instead of his left leg. I came in for the double leg from the wrong angle. His guard was up, but all he did was lift his knee as I was coming in for the double leg, and I just got smacked straight in the face. So I actually broke, my tooth is broken just here. I cracked the, took basically the bottom corner off my tooth and caught the knee straight up the side of my face. So that wasn't so fun. But working through pain is how we get stronger. So I think probably by tomorrow I'll have a really bad black eye. So what are we up to? Okay. Playing with new experiment. Oh yes. So Cable Tie just reminded me of something that Sion pointed out earlier. Cable Tie says, never fear, Cable Tie is here, playing with a new experimental watch I may have picked up from Sion this week. Something like this, perchance? Yeah, so Sion pointed out that he has just released an update on the experimental firmware for this. I think I've talked about this in the... Yes, I did. I talked about this last week, didn't I? So this is the... what I was doing was showing you pictures last week. Can I go to that camera?
The very same.
The very same, yes. Yeah, so this is the real thing. I was showing you... Last week I was showing you... Oh, hang on. I've got I need to have that. That camera should be alive now, except that it's got all the stuff on the screen. That'll go away in a moment. Yeah, what I was showing you was Sion's site, and this is the actual watch, which is pretty cool. So I think the board files are up already. I can't remember. And Sion is very rapidly working on firmware for it. Maybe, is this cable plugged in? Oh, it's only just not long enough. Maybe it'll reach. Will it reach? Let's see. Can I power it up? Yes. Okay, so you can just see on the edge of the camera. Tiny Watch S3 powered up. This is firmware from a couple of days ago, and there is new firmware. Is it gonna do anything? I thought it came up with a Wi-Fi thing. That's what I've seen it do in the past. Oh well. Anyway, reboot. So yeah, it's got a whole lot of stuff in it. It's got an accelerometer, right? Yeah, it's got an accelerometer so it can do step counting, and there's a microphone. One of the things that Sion has running on it is a screen that does, yeah, maybe it's just trying to connect to Wi-Fi. I don't know what it's doing. Anyway, there is a screen that does like a, see, my brain is not working today at all. It's got joggled. It does like a VU meter, anyway. Once firmware gets closer. Right, okay, cool. Oh, Wagon Load says, I had a tooth and earache all day today. Oh, that's not bad. If you've got tooth and earache, that's usually a sign of an infection. Oh, Wagon Loads asked, with a mic, can it work with Alexa? That would be cool. Oh no, because I said the word, she woke up, but now she's gone back to sleep. FFT visual display. Thank you, Sion, for using the words that are failing me at the moment. What? Henrik, this is a very random suggestion. Henrik said, could you build a levitating hot dog cooker for the next barbecue? Oh, James said, does it have a built-in oscilloscope on the watch? That would be awesome. I would love to have an oscilloscope on my wrist with a like a probe input or something on the side, so I could plug a probe into it and then use an oscilloscope. That would be super, super cool. A step up from the calculator watch. I've got an oscilloscope watch. What? As Jake would say, what? Yeah, scope watch. I'm... where are we? Where am I? I've got a whole lot of stuff open on my screen because I want to mess around with a little bit of coding. Oh, Chip says more donut holes, please. Yes, I hope you got the shipment of donut holes that Mitch would have sent you last week. Because I want to look at some of this stuff today. There was something else I was going to talk about as well, but I can't remember. So, Sion's watch, which is super cool. Oh, and the other thing that Sion sent me, I think you will be able to see this. I've just got to get the USB cable
Imogen Ann said,
stuck across.
Did you just make an Adventure Time reference?
Oh, no, it could have been you're right, it could have been an Adventure Time reference. It wasn't, but it could have been. So maybe I should claim that it was. No, it was a Brooklyn Nine-Nine reference. Alright, so this is the other thing that Sion sent me. This is the super blingy thing. And I put it in the case, and then I pulled the USB cable out, which means I need to reach the USB cable into the case and push it so that it engages. There we go, bling! And now it's being a VU meter, if I'm quiet. So if I put this in front of my mouth, it can be, I can be Bender. Stephen says 250 ml of coffee for John to help. Yeah. Yeah, Peter says...
Peter Lawler said, R.I.P. Andre Brower, sad face.
Yes, I know. I know. That's very sad. He was still quite young too. I think he was only 61 or something. Oh, that's right. That's what I was showing you. This thing, the bling. You should check this out on Xeon's online store as well. This is, I believe, an ESP32 S3 with an array of LEDs, and it does a few different things. Where are the buttons? Buttons on the side. If I press, which one? That one of these buttons. There we go. This one changes modes. So there we've got just a red VU meter. That's different colors, and then little different styles. It can be, yeah, this is more like Bender's voice, and then back to the original. So all different types of VU meter style. Very cool. There are a lot of LEDs on that. That's a very large number of LEDs in a very small space. Yeah, I know. Xeon says it's just some demo code it ships with. I know, you could make it do all sorts of things. Having a big RGB array like that in that little enclosure, it's kind of like a miniaturized version of a bedside clock enclosure. It's in this 3D printed case, and it looks really, really cool. I like this. I'm going to find something cool to do with this. So, thanks, Xeon. You should put the talking clock on it and add a speaker. Yeah, 320 LEDs. It's actually, I'm tempted to pull this apart and stick it under the, in fact I'm going to, stick it under the camera to show you just how cool this board is. It is, I certainly wouldn't want to be assembling these. This would break my mind, drive me bonkers. So it's a 320 LED array, and when you see how small the LEDs are, like you can see that this whole thing.
Peter Lawler said, "Happy birthday, Peter."
Happy birthday? Happy birthday to who? What did I miss? So take that out, put that aside, and check out this 3D printed case as well. It's got these little heat set nuts in it so that it's not just screwing into the plastic. Yeah, this is such a nice design. All right, now can I get this out? And this is the board. Look at this array of LEDs. You can see from the size of my fingers just how small these are. These are tiny. Each of these little RGB LEDs is tiny. And all this stuff on the back. So this is a double-sided load as well, which is something that I hate doing. I always avoid double-sided boards if I possibly can. So it's got 320 LEDs on this side, and then on this side it's got the ESP32, and looks like, oh, there's an SD card thing. Looks like it's got some battery management. Yeah, there's a battery connector, there's a speaker connector, I2C and stuff on there. Yeah, lots of small stuff. This is a cool board. So the whole thing is very small. This enclosure is way bigger than it needs to be. It's mostly empty space. The entire inside of the enclosure is empty, but you could put a battery in there, you could put a speaker in there, you could make it a little self-contained thing, which would be really neat. And, or alternatively, have I got this all right way around? I'm not sure. Alternatively, you could make a really slimline enclosure, because it doesn't need to be much bigger than this little front part here if you were going to leave power plugged in all the time. And it's got this diffuser on the front. Anyway, I'm not going to reassemble that right now. I will do that later.
Imogen Ann said it's Peter's birthday smile.
Yep. Xeon said it's so you can fit a speaker and a big battery. Yes. Oh, it's Peter's birthday. Well, happy birthday to Peter. Oh, Xeon said they are 1 by 1 millimeter. Those LEDs are 1 by 1 millimeter. it's a, yeah. So, Sion, a few years ago when you started Unexpected Maker, did you think you were going to be making boards like that? And this is, seriously, this board is a real achievement. It's what's gone into that to make that array, and the design of all of the stuff that's on this, the S3 with all the battery management. This is like a combination of all of the different little steps that you've over the years of all the different projects you've done. There are capabilities that you've built up, and the watch, of course, is another example of that. It's really impressive. Excellent work. Scott says, challenge, hand assemble one of those boards. No. No. I am not going to hand assemble one of those. Pick and place torture test, says Jack's Tech. Yeah. Well, you pulled it off, Sion. Good job. Okay, so moving on to much simpler stuff. What I was thinking of doing today, what I need actually is a piece of paper and a pen. I have pens. I do not have papers. What have I got? I've got a green pen. There's a red pen and a black pen. I've got some Sharpies here. I'm going to grab a piece of paper. Where shall I grab it from? This'll do. No, it won't, because I've already drawn on the back of that piece of paper. I need a piece of paper to show you the vague plan that I have in mind and why I'm about to do what I'm about to do. I need some space right about here, and some papers. Okay, now this is going to be one of those diagrams that is so simple that you wonder why I bothered to draw the diagram, but I kind of like to draw when I talk. Where's the edge of the page? Okay, so have, say, solder paste, and then I'm going to do a slightly cut down version here. Oven, PNP. This is just to give the general concept. It's not the not showing every element. So what the issue that I have at the moment is solder paste. Right now I'm doing it by hand. Well, more accurately, what I do is get Tommy to do it by hand. I say, here, paste these boards, and he uses a stencil and pastes it up. But ultimately what I need is some kind of a solder paste machine on here.
Imogen Ann said Jono, the artist.
Yes, I should sign my work. All right, here's the signature. X marks the spot. So I've got KO1, the first KO pick and place machine running. I've got two more KOs which are not in operation right now. There's the reflow oven, and what I need is conveyors between them, both to transport boards and to do inspections and hand placement of parts. Because once the boards have gone through a pick and place machine, you typically need to have a station in between where you can sit and make sure, firstly, you need to make sure the pick and place machine has done its job. And secondly, you need to be able to put parts on that the machine has not placed, but that you want to be on it when it goes through the oven. That could be things like ICs that you don't have loaded into a feeder, or switches or connectors or something. There's always going to be something that needs to be done as the board comes out of the machine and before it goes into the oven. So somewhere like around here, you need an inspection point. So a conveyor that is wide enough that you can sit at it and do things on the boards and see what's going on. So anyway, because I am a cheapskate, well, cheapskate? If I had money, I would spend it. I don't have the money, so I'm not spending it. I need a solution for the conveyors between all of these things. And this is the project that I started a couple of years ago to build a conveyor belt and a conveyor controller. And somewhere around here, in fact right here, this is the second prototype of the conveyor controller that I did. It's based on the WT32SC01 touchscreen. So this board on the front, is this attached? I don't think it is. Only the connector is holding it together, so I'll take it apart temporarily. There we go. So this is the touchscreen. It's got an ESP32 S3 on it, and these two I/O headers, which are actually identical. It's the same connections on both of them. They just give you two options in terms of how you want to orient anything else that you plug into this. So that's the touchscreen interface coming over here. So yeah, like that's the touch controller interface. This is the screen interface connected through to the ESP32. What is that? I wonder what that is. Is that USB to serial? Why would they be doing that when the S3 already has, I don't know. Or maybe this isn't an S3. It's a Rover B. Yeah, it's a long time since I've looked at this, so it's quite likely that I'm just straight up wrong. And it's not even the correct processor. So I think this may even predate the S3. These boards are a couple of years old now, although the S3 has been around for a while. Anyway, I think that might be USB to serial converter. So we've got USB on there. And this is the little add-on board that I designed. Copyright 2022. Yeah, so it was a couple of years ago. I think it might have been January 2022. It was around about that time. So almost 2 years ago. And it's got, hang on, did I solder? I've missed a couple of solder joints on that. Oh, that's an interesting catch. Quality assurance fail. So this board is like an I/O breakout for this board. I'm using the ESP32 that is on the touchscreen module and connecting through to its I/O, and then on this board providing the things that I need to build the integration with the conveyor belt. So what do we have? I've got to remind myself of this. So we've got a voltage regulator module. If I was doing it these days, this was like a very quick and dirty way of getting this working. And so I just threw down an existing voltage regulator module. And if I was doing this these days, I'd put on one of those voltage regulators that I've been using on lots of projects recently and just build it all directly onto the PCB. But this was like a first pass, take modules, throw it onto a board type approach. We have a couple of things. There is a CAN transceiver in here. This is the thing that is of interest to us at the moment. So the CAN transceiver connects to these two connectors. The connectors have...
R said that cap is tight.
Yeah, the cap is tight. It was the biggest one that I could fit in between there. So we've got positive and negative being passed along on that connector. You need a ground for CAN bus, you don't need positive, but this is just so that I can power a chain of these things all off the same power supply. So there'll be a cable that comes in from one side, this talks on the bus and then passes out the other side. So we can basically daisy chain a bunch of these together with CAN bus cables between them. And we've got CAN high and CAN low. Then I have two output drivers, X stepper and Y stepper, and it's got these 4-pin connectors on here for the stepper outputs. And what I did was break it out so that it uses these third-party, like the Trinamic style stepper motor drivers, and it uses those for moving the back rail of the conveyor so that the conveyor can adjust its width, and also for turning the conveyor to make it make the conveyor convey. And one of the reasons for doing this with these modules is I can either use a stepper motor module like this, or I can put on like a simpler module with just an N MOSFET or something on it and use it as or an H bridge for a regular motor driver. So the conveyor could use a stepper motor for its y-axis size and a DC motor to turn the conveyor, or it can use a stepper motor to turn the conveyor. It doesn't matter. We can, just by swapping modules, we can have different types of outputs. There's an e-stop connection there. I don't even remember how that works. CAN termination is there. So if this is the last item on the chain, on the CAN bus, then we can put the termination on it. Otherwise we take the termination off. Only the end devices on the bus have the termination. Up here there are a couple of opto isolators and a couple of relays. So these are little read relays. And the purpose of these, and these are connected to these little white JST connectors. What are these, JST PH or something? JST XH? I can't remember. I think JST XH. These are in and out, like ready in and ready out connections for the two sides of the conveyor. So conceptually, if you think of the conveyor as being like, if we're looking down on it as a plan view, we've got the two belts that the PCB sits on. So the PCB might be sitting here like this, and it's resting on the edges on the belts. And then there's the frame that holds the belts with the motors and things that drive it one way or the other. And that will be adjacent to two machines. So on one side, say we've got, what do we have? Okay, say we've got the paste machine there, and then we've got pick and place machine here. And we've got a board sitting here. The conveyor controller, so let's put the conveyor controller right here, sitting on the front of our mechanism. It needs to be able to talk to both, in both directions, to the upstream. So if we're imagining that, let me use a different color. So imagine that we have a left to right workflow here. The PCB comes from the paste machine, comes onto this conveyor, and then it moves into the pick and place machine. But the thing is, there has to be coordination between all of these. It's not enough just to have this conveyor turn on and constantly run so that anything that comes onto it moves in and then moves out to the exit. It has to be managed. It needs to communicate between the source of the board and the destination of the board. Because the pick and place machine might still be building the previous PCB. It might not be ready to accept a new PCB. So the conveyor controller has to be able to read the status of the pick and place machine to know if it is ready to receive a board. And so it's got a signal coming back from the pick and place machine telling it whether it's ready to accept a board or not. It also needs to be able to tell the pick and place machine that it has a board, because the pick and place machine might be ready for a board, but there isn't one here yet. It's a whole timing problem. And so what it needs to be able to do is send a message in this direction. I'll just use this for this overlay, the red. It needs to be able to send a message in this direction to the pick and place machine saying, hey, I have a board for you. Are you ready to accept it? So there needs to be that communication. So what I've been talking about here is communicating with the next step in the chain, but the same thing happens conversely on this side. The paste machine might have a board ready to send, but there's still a board sitting on the conveyor here. It's not ready to accept it. So it needs to be able to check with the conveyor, see if it's ready to accept it, and the conveyor needs to be able to communicate back and say yes or no, I am not ready to accept a board, or I am ready to accept a board. So often the way this works is there is no, so these signals, they're called ready in and ready out. Now this is something that I haven't done before. It's pretty much a very standardized sort of thing in production line type facilities, but I don't have any expertise in this. I'm just figuring this out. But what it means is, what do I use? yeah, so the signals that we care about are called ready in and ready out. And that is how these three devices communicate with each other. Now, yeah, anyway, that's what these are for. So because it's bidirectional and I didn't really know how I wanted to hook all of this up, what I've got is relays on the outputs. So our conveyor controller can fire a relay, because typically this communication is done using like just dry contact type stuff, because you might have devices from different manufacturers, like a solder paste machine, the conveyor, and the pick and place machine could come from totally different manufacturers, and you need to be able to hook them together. So they just use dry contact connections. And so this is providing two relay outputs, one in that direction, one in that direction. And it's got opto-isolated inputs. So one input coming from this direction, one input coming from this direction. So that gives flexibility of the controller to be able to talk to both the upstream and the downstream devices. Yes. So I have not been looking at the chat, but I think it looks like there are some interesting things popping up in the chat, and probably people who know far more than me about what is going on. Okay. Mitchell says 2022 is only 1 year ago. Henrik said, have you searched conveyors in AliExpress? It's only like 60 euros here. What? No, they're like $2,000. If there is a 60 euro conveyor that can do all of this stuff, I would stop this project right now. So I would really like to see one. Where are we? Where are we? Wagon Load says, I would like something like that to make a wireless 3D printer. Not sure about that. I don't understand. Sorry, Wagon Loads. Jackstack said, does the e-stop cut power? I actually do not remember how the e-stop works, but let's refresh my memory. And because I happen to have it open right here, I'm going to close that. And e-stop input. Oh no, it's just this particular one is not an electrical e-stop, it's just like a software e-stop. So it's just an input going to the ESP32. So yeah, there should also be a hardware e-stop which is cutting the main power to everything, so that everything just stops and there is no reliance on software intervention or controllers driving outputs to stop things or anything like that. So my plan when I wire all of this up is that there will be a proper e-stop button on the main power, so that if you hit that button, it kills power to all of the devices powered down the chain. So the CAN bus, like the daisy chain cable that links everything together, that will provide power to the conveyors. If you kill power to that, it'll kill everything. Everything will just stop. But at the moment, that e-stop input is a logical input. So I think I figured I could use that. It was one of those things where there was an extra I/O pin, so I just stuck a pull-up on it, put a connector on it, and say, all right, that can be an extra input that we can use for a stop button if we want to. Not a safety critical kill all power emergency stop, but a make it stop in software stop. All right, now y-axis limit sensor. Okay, so there are some other sensors and things that we'll get to. I saw in the chat there was a question about sensors, and I will get to that in just a second. Yes. Does it need a limit switch for Y? Keith asked. Oh, yes. That's what this is. Y-axis limit sensor. And this is using... So at the moment, this is just a connection on the board. In fact, where is that connection? It must be on here somewhere. Where is... Oh, there it is. Y limit. Yes. Hang on. I'll switch back to this camera. It's hard to see on this shot, but there is that little yellow pin header there. That is the Y limit input. So it's signal, 3.3 volts, and ground. And I think from memory, I deliberately put 3.3 volts in the middle on that. So if you plug it in backwards, then it doesn't matter. And you can see a yellow patch wire across there as well. I'm pretty sure I've revised the PCB since then. Oh, that's right. This chip here, that is an MCP23017, which is being used as an I/O. Well, it is an I/O expander. And the reason that I've got that on there is despite these huge connectors on this touchscreen, the number of I/O pins on this is quite limited. And I needed more because I needed ready in, ready out upstream, ready in, ready out downstream, and stuff. I just needed more stuff. So that is an I/O expander, which is used to give us more, just more. What are we looking for? This. Okay. So Y-axis limit sensor. Yeah, that is used for homing the conveyor. And this is all working. So I got this conveyor mechanically and in terms of mechanically, electrically, and in terms of software, I actually got this conveyor fully working nearly 2 years ago. It has been sitting in my workshop ever since, and I've just never really finished off the job. Partly because I didn't yet have the machine for it. So when I started working on this, I don't think I even had the KO pick and place machine. No, I didn't. I haven't gone to Canberra to get the KOs yet. And so this was kind of a speculative project. I started working on it knowing that I would need it, but then didn't actually get to the point of needing it. And now I need it. So yeah, I could send it G-code and tell it to go to a certain width and it would do that, and I could tell it to run and it would do that. It was actually kind of functional. But what I need to do is add CAN bus support. Okay, so this comes back to part of my explanation of the architecture. Now let's see what's on this other sheet. Ooh, CAN bus interface. There we go. What else have we got? PCB sensors. Okay, this is another thing. Oh yeah, so we've got ready in out left, ready in out right. There's the opto-isolator circuit, and there is the dry contact relay output. One for the left connection, one for the right connection. Then what have we got? Main power switch, that will kill power to it. And PCB sensors. Okay, so this is another critical part of it. I will get back to the comms architecture in a minute. And there is also a question about stacking multiple boards on the conveyor that Stephen asked. I will get back to that. That is a very important thing. So, where was I? PCB sensors, that's right. Where did the PCB sensors go on this? I actually can't see the connectors for it. Is that something I added? GPA 0 X shot, GPA 1 X shot R, X shot L, X shot R. Maybe that was something that I added. I think it must be. So this version of the board that I'm looking at right here, this is the V1.0 board. I think that the version that we're looking at that I just had open in Fusion is the revision that I did after this, which I haven't fabricated. I haven't ordered the boards. But what I did was add, so I applied that fix, that little yellow wire that goes across there. That has been patched. and I also added PCB sensor inputs. And that is because the conveyor needs to know when a board has arrived or when it is at the exit. So the way that happens is you have something like a little sensor on the right near the start of the conveyor, and you have a sensor near the end of the conveyor. And so when a PCB starts traveling onto the conveyor from the upstream source, the conveyor controller connected to that sensor, I probably should have diagrammed the sensors as being on the front. The conveyor controller can detect, yes, a PCB has just entered the conveyor, and then that gives you a few options. First, it means that you've got something that you're moving, and secondly, it means that you can, if you have control over the speed of the conveyor, so you know how far it has traveled, it means that you can bring the board to a certain point and then stop it. So you can queue up a board here. What you can do is, if you've got a board that is ready to come in from the left, but you don't have a downstream ready to accept it yet, you can have the board come onto the conveyor, move to the midpoint somewhere, and stop. Now, it also means that you can tell when the board has gone past, because the sensor will detect the leading edge of the board, and then as the board is coming on, it'll continue being triggered, and then once the board has gone past it, it'll stop being triggered. So you know that you've got past the back of the board. And then what you could do is potentially you could stack multiple boards on here. So you could have a queue of boards on the conveyor, because when the next one comes in, it could start moving, and this first board will continue moving. You'll have a little gap between them, and then you know when you got to the back of the second board, and then you stop again. So you could end up with a couple of boards on here. Now, there are complications with that, because yeah, lots of potential complications, but it is possible. And then the sensor at the end of the conveyor is very useful in a couple of ways, including one that I didn't even think of until I started using the KOs. So what this allows you to do is detect when you've got a board that has come up to the exit point. Now, that would allow you, in that scenario I was talking about before, if you are loading multiple boards onto this conveyor and you're queuing them up ready to go to the next stage, you could know when your board has reached the end and then stop, because you know that this machine is not yet ready to accept it. You've got to stop your conveyor.
Says no, no, no. Trust me. One board on a conveyor at once.
Yeah.
Say it again.
One board on a conveyor at once. Okay. So you could then stop it at this point. But this is one thing that is really interesting that I've noticed on the way the KOs work. So internally on a KO, they basically have this mechanism. They've got this conveyor belt, and they've got a sensor on the input side, and they've got a sensor on the output side. So they know when they start ingesting a board, or they know when there is a board there that is ready to bring into position. And they have a sensor on the output. Now, the interesting thing about the way the output sensor is used is that it's used as a safety inhibition on homing the conveyor belt. Because what happens is that when the machine starts up, now imagine for a second this isn't a conveyor on its own, this is a pick and place machine. So imagine that this is actually a machine that we're looking at, and it's all enclosed. Now, when the machine starts up, so the front rail is in a fixed position. The back rail can move backwards and forwards to adjust the width to suit the job or to suit the board that you're putting in. So, in order to, unless it's got some kind of a closed loop positioning system, which I'm sure the more expensive machines do, my machine, the KO, doesn't. It has to home that rail. And the way it does that, I'm going to grab a different pen, is that there is a limit switch just here, down near the front right of the machine. And you can imagine that, so imagine that this front rail is fixed. This back rail, I'm going to draw some slides here. So this back conveyor can slide backwards and forwards. There is a stepper motor that moves it backwards and forwards, just like the y-axis on a 3D printer or something. So what it does is when it wants to home the machine, it brings that back conveyor rail forward until it trips this sensor, and that is the minimum position. So at that point the conveyor is quite small. That is as small as it can possibly get for a small PCB. I don't remember what the smallest is, but it's probably like 20 millimeters or something. It's 20 or 30 millimeters. It's quite small. So that back rail moves forward and it trips this homing sensor or the limit sensor, and it knows that's at 0 position. The controller knows the gap at that point, and then when you tell it to go, say you've got a panel that is 220 by 235 or something, whatever the thing happens to be. So say it's 220 millimeters wide, 230 millimeters, 235 millimeters deep. You tell it to go to 235 millimeters plus a margin for movement. You need to take it to like 236 or something, whatever the margin is, so that it doesn't jam in there. Then it adds the offset and the distance that you've requested. So say that was 30 millimeters. You tell it to go to 235, it moves 205 so that the gap between the two conveyors is correct. All right, this is all basic homing stuff. That's not the important bit. This is the important bit. What happens if the machine has been shut down? Could be like an e-stop situation. It could be, anyway, lots of reasons that it might have been shut down with a board on the conveyor. That can happen. So what happens is on the KO, when you send it a homing command, the first thing it wants to do is bring the back conveyor forward to home it on here. But that's dangerous, because if there is a PCB sitting on the conveyor, that's just it's going to jam, and it's going to possibly break the mechanism because it's trying to move the back rail forward. So the first thing that it does before it does anything else is it turns on its conveyor heading in that direction, and it runs it for a predetermined period of time. Basically that time is at least as long as it would take for a board to travel from the entrance of the machine to the exit of the machine. So say it would take 12 seconds for a board to go from here to here. Just based on the rate of the feeder, rate of the conveyor. Then it runs it for say 15 seconds, and during that time it's watching the exit sensor. And if it detects that a board has hit the exit sensor within that time, it stops the conveyor immediately and it throws a warning, and it refuses to continue homing the machine because it knows that there is a board sitting there and it's not safe to move the back conveyor rail. So the exit sensor is very useful for that. So conversely, if it runs its conveyor for the 15 seconds and nothing gets to the exit sensor, it then knows that the conveyor is clear, because anything that would have been on it would have got to the exit sensor by then. So it then stops the conveyor and it moves the rail and it proceeds with its homing process. So having the exit sensor is very useful for that point of view as well. And that's not something that I anticipated. Like, I just hadn't even thought of that. But that's the way the KOs work, and I'm sure that's the way a lot of other machines work as well. So that is a very useful thing to implement. So in the firmware for my conveyor belt, I want to implement something similar to that. Have it, when you send it a homing command, make it try to clear the conveyor, and then only proceed with homing after it has actually done it. Now in my case, my conveyor actually homes to the back, not to the front. The KO homes by closing as far as it can until it hits the sensor, and then moves back out to the position you want. My conveyor has the homing sensor at the back, so when you tell it to home, it opens, which is less dangerous if you happen to have a PCB on it. But what will probably happen is the PCB will fall through the mechanism. and like it could just fall clear and fall on the floor. But if it happened to be over one of the cross rails at the time, it might fall and then sit on it, and then when you try to bring the back rail forward, it'll jam up again. So it really is a good idea having that safety of making sure the conveyor is clear before you try to home it. Okay, back to the chat. Back to the chat. What is everybody saying? Where are we? Sion said, it's supposed to stop at the exit, second sensor, or do you want a mid-stop for inspection? Aha, okay, so this is the, this is where I want to make a change. I want to, oh, Dentistries is here. Good morning, Dentistries. Dentistry said, I do something similar with the e-stops for my robots. I use a phonotype connector as a standard and a series of relays to cut power to everything. Yep, cool. Now, so Sion was just talking about having a stop at a midpoint for inspection. Yes, and partly the reason, that is partly the reason that I wanted to redesign my mechanicals to go away from a DC motor to a stepper motor for controlling, for driving the actual conveyor. So the right now, in fact, I'm going to go and grab one. What will I do? I'm going to stick you with a down view of that diagram just so there's something on the screen. I'm going to go and grab one of the conveyor prototypes from the far end of the clean room where it's currently sitting, because this is the sort of thing where, you know, waving my hands and drawing diagrams is probably less effective than just showing you the real thing and explaining my thinking behind it. Oh, it's all dusty because it's been sitting, yeah, it's been transported around. I don't know the best way to show this to you. I think I'm going to try using the front camera. Okay, so this is, I could use the overhead camera and zoom it way out. Which way? All right, so this is one of the prototypes. I've done a couple of prototypes of different lengths. This one is kind of a longish one. I can't remember how long it is, like the left to right width. I've done another one that's really short as well, which is intended to be a joining conveyor between machines.
More cameras.
Yeah, I do need more cameras. So the thing is that when you join machines, you need space between them. If you've got, say, two pick and place machines, they have conveyors built in that come only just past the housing of the machine. And if you put the two machines hard up against each other so that the conveyors meet, it's basically a really bad idea, because you need to be able to get access between the machines. If anything goes wrong, you've got to be able to get in there, and it's hard for alignment, and yeah, it's bad for all sorts of reasons. So you need at least some kind of a short conveyor segment between the machines to give you access in there. And so the other version of this that I made is very similar to this. Oop, how do I hold this? Except that it has shorter rails, like it ends here and here, so that it's a joiner conveyor instead of one that allows you to actually get in. All right, so what can we see here? You are looking at that from the front of the conveyor at the moment, the front of the machine, and this is the fixed rail. So this is where the, yeah, so it's the front of the conveyor belt. This is the back rail, and the back rail moves. You can see it's got these, yeah, it slides along here. I'm like, oh, can I move it? Yes, I can. Okay, I'm just back driving the stepper motor. So there is a, okay, I am going to try to do this with the overhead camera because I think that would be easier. I'm breaking it now. All right, overhead camera, except that it's way too zoomed in. So let's go for zoom out. That's as zoomed out as it gets. And it may be slightly out of focus, I'm sorry. Which way around? I'll turn it around so that it's facing us for logicality. All right, so front rail, there is no actual belt on this right now. You can see that it's got end caps for where the thing mounts, and you can see here, this is, oops, there. That is where there would be a roller, so there would be the other belt going around that. The back belt is on it though. You can see this green belt, that's a anti-static belt out of a pick and place machine. Runs around this roller. There's a little motor inside here. That's what makes the conveyor move. And at the other end, it is around a roller with some bearings and things. And this, hang on, how do I get this in position? Okay, so this moves backwards and forwards. You can see it sitting on those linear rails on the sides, and it's got a belt going around here and stepper motor, oops, stepper motor at the front. This is one of those, what are they called? The J28JN something steppers. I can't remember the part number. So there's a stepper motor in there. And then under this cover at the back, that is an optical limit switch. I just got this cover over it to make it neater. There's the optical limit switch. That's the Y-axis limit. And then this little 3D printed thing here off the back, as it drives it back, hang on, I'll take that off. As it drives it back, it comes in through here and it intersects the limit switch, and that's how it knows that it's got all the weight at the back. Oops. It's skipping on the belt. This whole thing is a bit loose at the moment. And also I shouldn't be back driving it by just pushing this. So yeah. Oh, and you can see there is a little drag chain on here. It's a tiny little baby drag chain, really cool. And that takes, so there's a cable that goes from the machine, front of the machine, goes through the drag chain, comes up here into the back of this cross piece, and it goes inside the cross piece and comes up to this motor, because there needs to be a motor for the front belt and a motor for the back belt and a motor for the front belt. So we need that drag chain to get the power through to the motor. Okay, now that I've shown you all of this, what is inside here? In fact, I'll take the front one off and show you what's going on, because this is what I'm going to be changing. And I know this is a very long-winded thing, but this is getting back to Sion's point from ages ago. Okay, so this is the little mechanism. Now I can zoom it back in. And hang on, I've got to fix focus, so I'll put it into focus assist mode for a moment. And then it will jump back out again in a second, and you'll be able to see the bigger picture. 3, 2, 1. Come on camera. There we go. Okay, so this is a 3D printed mount for the motor. So there's a little DC motor in here. You can see it's just got red and black leads coming out of it. And where's a screwdriver? Right about here. All right, so there is, what is this motor called? I can't remember. They're the super common little motors that are used in all sorts of things. Oh, that cover doesn't really help because it's screwed in from the front as well. But anyway, the point is there is a little DC motor inside here, and when a, yeah, I've got a 3D printed sprocket that goes on there. I'm going to stick this back on.
1 hour remaining.
But the thing is that driving a DC motor is, you can calibrate it to set the speed, but it's not as nice as having something like a stepper motor where you know exactly how many steps it's taken and therefore you know how far it's traveled. So with this, okay, getting back to this diagram, Zion's question was, do we want a sensor, oops, in the middle here somewhere, like an intermediate sensor? So we could have an entry sensor, an exit sensor, and an intermediate sensor. So that what we could do is bring a board into the middle position of the conveyor and then stop. And that is extremely useful for inspection, for example. So if you've got an inspection station, you want to bring the board to the middle. You don't want to take it all the way to the end and then stop it at the exit sensor, because it'll be sitting off on the right-hand edge of the conveyor. You need to be able to bring it to a known position, or pretty close to a known position. So with the DC motor controlling this, if you have this running at a known speed, so you know how many meters per second, and of course it's going to be a fraction of a meter per second. So say this is running at, it's probably going to be something like, well, actually I can't remember. I'd just be telling you the wrong numbers if I said stuff. The way my current reflow oven, I think, is running at 0.2 yards per minute. It's a German controller on an American oven in imperial, using like imperial measurements. So I may be totally wrong with the number there, but I think it is 0.2 yards per minute. So, but no, that's it. I was going to say that sounds too slow, but no, that's probably kind of in the ballpark. So it takes 5 minutes to travel a yard, which is a meter. Yeah, that's probably not far off. So 5 minutes to travel 1 meter. Now these conveyors are going to be a lot faster than that. The reflow oven could be running quite slowly because boards have to take a while to get through it. But the conveyors between the other machines can be moving faster. So say it was moving at, I have no idea. It's probably faster than this. But say it was 1 meter every 5 seconds or something. You know, it's going to be something in that region, just based on how fast I see the pick and place machine conveyor moves. So yeah, if you have a known rate of speed, and ideally you want these to match up. So whatever speed you've got running on your conveyors, get them to match. They don't have to match exactly, but when the board travels over from one to the other, it'll accelerate or decelerate as it moves between the conveyors if the speeds are mismatched. As it grips from, like, loses its grip on one and grips on the next one. So if we have a known rate of movement of the conveyor, and a board hits the entrance, and we know that it takes, say, 3.8 seconds to reach the center point of the conveyor, then the software can just say, oh, okay, I have tripped a timer, 3.8 seconds later, stop it, and then you stop the board at that position. So that was going to be my approach with the DC motor method. But then I figured if I put a micro stepper motor in here instead, it gives a lot more control. It means that I don't have to, well, it means my tuning is a lot less of a hassle, because with a DC motor, I'm basically just going to have to do a bunch of experiments and see if I modulate this to a certain duty cycle. Say I'm running 12 volts or something through this DC motor, and I modulate it at a 50% duty cycle, how fast does the conveyor move? I'd have to empirically do a series of measurements and figure out like a calibration curve to be able to say, I want the conveyor to run at a certain speed and then have it drive the motor using that calibration.
Unexpected maker said, bad idea. You have to sue a sensor. Otherwise, what if the board is midway and power goes out, and then you can't detect if a board is there when power comes back on?
Ah, good point. Okay, so if you couldn't hear the speech since then, Sion just said you need a midpoint sensor, because what happens if power goes out and then you've got a board sitting in the middle of your conveyor and you bring power back again and the conveyor won't know that the board is there. So that is true. if you don't also do a homing cycle. So if you did a homing cycle, it would try to eject the board first, trip the exit sensor, and then it would know there's a board there and it would stop the homing cycle. But being able to recover is really important. This is something that I've kind of been thinking about a little bit, but I don't have all that many clues about. So one of the things that I have to think about is if I end up in...
Maker said, see my second comment too.
Okay, cool. Yeah, sorry, I haven't been reading chat for a little while. I should switch back over to here. In fact, to here, just because that's more interesting to look at. Okay, so I'm going back to... I'm back behind in the chat. KOI uses the 2-wire SMEMA. Okay, cool. Getting back in the chat. So there is some interesting stuff here. So Sion said, all machinery understands SMEMA, a basic or very complex plus or minus 24 volt status system, and said the KO uses 2-wire SMEMA, all the Chinese machines do, and my Juki can support 2-wire, can do 2-wire SMEMA, but can support up to 16-wire. And my conveyors, stencil printer, loaders and unloaders all do SMEMA. Yeah, cool. All right, I need to learn about that stuff, that's for sure. Otis is designed to detect a PCB, has come in to inspect, but it can't be used to adjust the width of the conveyor as the board would already need to be on the conveyor. Yep. Yeah, so Scott said, how about a sensor every, say, 5 centimeters along the conveyor and inspection point is reached when an equal number are clear at each side? Yep, and Wagon Load says, if each PCB has an unknown length, you need to detect the trailing edge to know when you got the PCB centered. Yeah, so that both of those are valid options. I was actually thinking of Wagon Loads' method. So Wagon Loads' thing is PCB enters, and the PCB is of an unknown width. You know when it has tripped the entry point, it keeps moving, and then you see when it has tripped the exit point, and you know how far you've moved it, which means you know the width of the PCB, which means you can calculate where to stop it to get the center of the PCB in the middle. That was the method that I was thinking of using. Yeah, so going on to what Sion said, so this is what was read out earlier, is bad idea, you have to use a sensor, otherwise what if the board is midway and power goes out and then you can't detect if a board is there when power comes back on. Also, what if there's a board there and the entry sends a new one because it doesn't know you're inspecting one because no mid sensor? Yes, that would rely on some kind of a software flag to know that there is one that hasn't been ejected yet. So there'd need to be some kind of a state machine in the control software. But you are right. I think, Sion, you are talking me into adding support for a mid sensor. So I don't think I would go to the trouble of putting sensors like all the way along at little intervals, but I can see the value in having a midpoint sensor. So what it could be is a combination of methods. In order to get the PCB to the center of the board, using the method described by Wagon Loads, where you know the entry point.
Maker said, but if you use a software flag, it makes the conveyor 100% incompatible with every production line machine ever made.
Yep. Yes, maybe. But the communications with other production line machines come from the controller. And if the controller is remembering its state of, yes, there is a board there, then it'll still communicate correctly with upstream and downstream. But yes, okay, I am leaning now towards adding a midpoint sensor. So when the board comes onto the conveyor, you can measure the width of the board because you know when it starts and when it finishes, and then move it until it trips the midpoint sensor, and then move it half the width of the board again, and then stop it. And at that point, you've got the board centered on the conveyor, and you know that the board is there because you can measure it. Your sensor is under the center of the board. So I think I am going to add another PCB sensor. So I'm going to have a left sensor, a right sensor, and a middle sensor. Now let's have a look. I'm going to remind myself of what's going on here. So before I send this off for fabrication, I think what I might do is replace the power supply. I don't know if I can be bothered. Now where are the sensors? Out, in, limit, e-stop. Where on earth are they? I actually can't see them. Let's go to this. Limit sensors, in, out, R sensor, L sensor. Oh, hang on. Were they on the other board? Where is that board? Oh, they were there. They were so obvious that I just did not even see them. Okay, hang on. Why is it that connector? Hang on. What am I running on there? So I've got 3.3 volts, ground, SEL, SDA. Oh, and the shutdown. Okay.
Mitchell
This is a
said
trick.
Another way to handle sensors is, instead of having 3, you have a row of IR LEDs that span the length of it. You can tell exactly how long a board is, where a board is, and for homing.
Yes, I could, but mechanical assembly would be more annoying, I think. Okay, so that's right. This is I am remembering now what was going on with these sensors. We'll get back to that in a second. But if you look at this, see this this huge connector right here, and it even says R sensor and L sensor. Those are the connectors to the sensors, because I was just going to use IDC cables and IDC plugs. But that is kind of annoyingly large. I might switch to, I don't know, like 2mm IDC or 1.27mm IDC or something for those connections. Xeon says,
Unexpected Maker said, if you really want a center inspection point, regardless of sensor or software, you need 2 conveyor sections, 1 2/3 S in length, so it covers inspection area, and 1 1/3 on exit.
yeah, a multi-section conveyor. Yep. And the way a lot of them work is that they'll actually have 3 segments. So there's an inlet segment, a middle segment, and then an outlet segment. And essentially it's 3 conveyors all joined together.
Said, so you can control one coming in and inspect, but have one waiting to go into the PNP.
On the second
conveyor.
Yes, exactly. On the exit conveyor. So you can send it on and have it sit in the queue and then bring the next one in, which is effectively like having multiple conveyors all stacked in a sequence. It's just that they're physically, mechanically in the same mechanism, all under the control.
Mitchell said, well, if the control board is just one part of the IR array, then you can minimize setup process. So easier to build the units of multiple lengths.
Maybe. I don't know. I'm not convinced about having all of the IR sensors all the way along it. I think having 3 board sensors is enough. So, no, Xeon, don't stop.
System notification, 45 minutes remaining.
No, Xeon, you're the one with the experience with this. You've been doing this hands-on, real world. You know the pain points. So, don't stop. Oh yeah, so Xeon pointed out IR won't work properly with different solder mask colors. Oh, and Henrik said, but the ESP32 and camera ID are back up there. So previously, sorry, I didn't read this comment out, but Henrik suggested using an ESP32 cam as like an optical method of detecting boards. But I think that might be a whole lot more work and complication than necessary. So the okay, using a camera-based detection system, I think is overkill in this situation when you see how simple these sensors are and how cheap they are. So these limit sensors, the things that are connected on here, do I have any here? I probably do, but finding one, who knows? They might be sitting right here and they might be impossible to find. I could be looking for the next 10 minutes. So I don't think I'm going to waste much. No, I'm not going to waste any time looking for them. Oh, and there is one. Is that it? Yes, there is one right there. Okay, so these little sensors, these thingies that I'll rip one open and chuck it under. I can't remember how much these are, but they're cheap, whatever they are. Let's go back to here. These little modules, this is where we need lots more zoom inage. In fact, I wonder if we can go for, yeah, let's do this. I'm going to switch cameras in a minute. V53, these are little time of flight sensors, I think. So this, I've got to fix the focus. There we go. VL53 LO. So this is a little time of flight sensor. It emits, I think this one might be IR, I'm not sure. So it emits and then detects when the thing is reflected. Now I wonder if Sion's comment about not detecting red boards or some types of boards might be affected by this. This is something that I should test. So it's got the driver circuitry on the back there. Well, driver, I think it's a voltage regulator and just a open collector or output or something.
Maker said they are laser based.
Oh, laser based. Okay, cool. Thank you. So this thing, it's got V in ground, SCL and SDA because it's I2C. Oh, GPIO 1. I wonder if that's connected to the transistor. But anyway, I don't really care. And then X shut. Now, the issue with these things is it's an I2C device, but you might notice that nowhere on here does it have somewhere that you can set an I2C address. And normally what you would have with an I2C device is you set a different address for each device, and then in your software you can say which one you want to talk to. These ones are a little bit oddball. What they use instead is they have effectively an enable pin or an inhibit pin or whatever you want to call it, called X shut, which I think is a funny name for it. And what you can do is use that. It's kind of like, it's weird because it's kind of like a cross between SPI that uses a chip select pin for each of the devices on the bus and I2C. So what you do is you have multiples of these sensors on the same I2C bus, so they're sharing SCL and SDA, and then you have control of each one using X shut so that you can turn it off. So what you do is you turn off all of the sensors that you don't want to talk to and only turn on the sensor that you do want to talk to, and then you can talk to it over I2C. So in some ways it's clever because it gets around the address issue, and it means that you can have many of these if you want to. But the downside, of course, is you need an I/O pin for every one of these sensors so that you can enable it. Anyway, so these little modules, I wonder how much they are. I'm going to check it out. Let's see. I can't remember. I would have just ordered them on AliExpress or something like that. I'm going to VL5. what's the part number? VL53 LO something or other. Time of flight sensor. Oh, $15 from Adafruit. $3 from AliExpress. I'll bring this up on the screen. Hang on. It's a different color, but it's basically the same sort of layout. It looks like an updated version of... No, don't allow. Stop that, AliExpress. So this is a laser ranging flight time sensor module, distance 400 centimeters. And this just looks like a slightly updated version of the ones that I've got. Pretty cool. Anyway, yeah, so you can see $4.68. So shipping $1.76. Okay, and what happens if I get multiples of it? Does shipping go up linearly? $3.67. It does. So they're padding the price with the shipping. Or 3. If I go to 4, no, the shipping isn't going up. 5. Okay. Anyway, so a couple of these. And this is a much simpler solution than using something like a camera for, okay, so say $5 per sensor. And like, I haven't looked around. This is...
said there is an I2C I/O expander chip that allows you to address multiple I2C devices that have the same I2C address.
Yes, that is true. Yes, you could do that. So you could have them all enabled all the time. If you couldn't hear that, Wagonload said there is an I2C I/O expander chip that allows you to address multiple I2C devices that have the same I2C address. Yes. Yes, that's true. So that would be another approach to this. But what I did was I just brought out a couple of I/O pins, and they are, just judging by the fact that there's a diode in there, looks like these are kind of like an open collector type thing. So you pull this to ground and it disables, I can't remember which way around it goes. I think it's, if you pull it down, it disables the sensor. If you just leave that pin floating, it'll be enabled by default. So what you can do is disable all the sensors you don't want to talk to. So I need to add another PCB sensor. I need to add an intermittent one. Oh, David asked, got a link to that expander chip. Not off the top of my head. Oh, Henrik said, could you have used something like ultrasonic sensor to measure the distance? Yes, but it's physically really big. These things are tiny, and this needs to mount just under the edge of the conveyor, looking up at the PCB. And they're probably about the same price as an ultrasonic sensor, and they're a fraction of the size. So, and also they work pretty well at short distances, so I think they're better. Now where is... Oh, okay, so Mitchell has already dumped the part number. Thanks, Mitchell. So PCA 9548A. This is an 8-channel I2C switch from Texas Instruments. It allows you to connect up to 8 devices with the same address. Yeah. Oh, Henrik said, I meant measure the midpoint. No. So you're talking about measuring from endwise? No, there's too much mechanical structure around it, and you're trying to measure the end of a PCB. So yeah, I don't think that would work. Oh, Pato, welcome. So what am I doing? Okay, I think I'm going to add another, before I fabricate the next version of this board, I'm going to add a midpoint sensor. So I'm just going to add a note to myself. Start adding some notes. So it is going to be to do I may have a to-do list on the first sheet, I don't know. To do, add midpoint sensor. I haven't even gotten into any coding yet. I've actually got Arduino IDE open right now because I was going to start adding some CAN bus code to the controller. All right.
Mitchell R said just add 2 sensors if you can. Then if you need to add anything else, it is already ready for you.
Yeah, so maybe I should be future-proofing myself by just adding a spare thing. Yeah, that's a good point. That could be useful. That could be useful in. No, I'm thinking about Xeon's Xeon structure where you've got 2 conveyors combined. So you've got the entry and the inspection point, and then an exit conveyor which is shorter. I would probably need 5 sensors for that. So I've got entry on the start, I've got the inspection midpoint, exit on the first conveyor, entry on the second conveyor, exit on the second conveyor. So that's 5 sensors. To do, add midpoint sensor. And I'm going to say maybe add spare sensor. What else did I need to do? Replace sensor connectors. What should I use for the sensor connectors? What I need is something that is... Okay, so I need 5 pins because I need power, ground, SCL, SDA, and the X-shut connection to each of the sensors. I used just regular 2x6 IDC connectors on there. I need something smaller. Maybe
Mitchell R said fix bodge on board. Use those green, black, orange screw plug-in terminals. More flexy.
Okay, so 2 things. Fix bodge on board. Yeah, that has already been done. This is... Where are we? Oh, it only says V1.0. Yeah, I'm going to have to check. Maybe I'm misspeaking. I very confidently said that fix has been done, but maybe it hasn't. I need to check what that patch wire is, but my very fallible memory very confidently says that I had already fixed that on the board. But the version number hasn't been revved, which means...
Unexpected Maker said, okay, this is way more complex than any of this. Do you really want to know the next problem?
I sure do.
Mitchell R said, dum dum doom.
Okay, I need to know all the problems. Please, please tell me the next problem. So... Look at the size of these connectors. Now, okay, so getting back to, who was it? Mitchell said, fix the bodge on board and use those green, black, orange screw plug-in terminals, more flexy. What do you mean by green, black, orange screw plug-in terminals? Are you talking about for the sensor? Because I'm already using the plug-in screw terminals for all of these other things. Like this connector here, this CAN bus connector. That is one of these. Go Magic Overhead. So this, you can see, that is a pluggable screw terminal. That's what I'm using for the CAN bus link coming through it. And so I laid this board out in such a way that I can either use vertical pluggable terminals, like I've got mounted on this board right now, or you can have horizontal pluggable terminals so that you could have the cables coming in from the side. And you can see there's actually a notch in the PCB, it's only a very small notch, it's only like 2 millimeters, to allow this. So if this was right angle, the CAN connection would plug in from the end.
System notification, 30 minutes remaining.
But then I decided that if this was...
Same thing, but smaller version. And if you have to change sensor or whatnot, Easy to just wire something in.
Oh, you mean there are small pluggable screw terminals? I want those. Okay, so yeah, I decided that if all the
Unexpected Maker said SMEMA is dumb, can't make it smart, and compatible. Either a board is on the conveyor waiting to go to the next spot, so it's at the last sensor, or it's considered empty and can take a board.
Okay. So SMEMA is dumb. Yes. So this gets back to where all of this started. My plan was to use CAN bus for all of this and to make it smart so that the system knows where the boards are in the chain, bidirectional communication, and it can send commands like tell a conveyor to move to a certain width. I'm going to get into this in a minute. So I don't think I'm actually going to do any coding today. That was my plan, but I will at least explain what I have in my mind for how this is going to work from a communications point of view. So I'm tempted to dive straight into that, but I will resist it because I want to figure out, yeah. Oh, Sion is about to say.
Unexpected Maker said, so that means if you stop a board to inspect and tell the previous machine it can't take one, then the next machine can request it and if it doesn't come, it will time out and stop the job.
Yeah, okay, so that is a problem. That scenario is the sort of thing that would be quite likely. Yeah, if a machine times out, there needs to be a better way of coordinating them. It sounds like SMEMA is very basic. It's just signaling up and down the chain, and what I'm wanting is more coordination of the entire chain, and yes, I'll get to that. Oh, DIY says, dinner time here, we're having a barbecue, anyone want some? Yes. I actually had barbecue twice yesterday. I had my gym's end of year barbecue up on the top of Mount Dandenong, right next to Sky High Restaurant, and so I had barbecue in the afternoon and then went into the city for Korean barbecue with a client for end of year.
Peter Lawler said food o'clock.
And pretty much. Oh, Henrik says, look in Discord, I think I found the mini plug-in terminal blocks. All right, so this is the squirrel that I was wanting to chase, because I really like those 3.81 millimeter pluggable terminal blocks, and I know there are 3.5 millimeter as well. But let's see. I'm going to click on this link and leaving Discord. Yes, I want to leave Discord, and I will bring this up on screen in a second. Which button do I press? That one. All right, what have we got? 2.54 millimeter pitch PCB screw terminal. Yes, that's cool. It's kind of like the ones I've been using, but smaller. I should order myself some of these just to mess around with them. So, Mitchell, is this the type that you were talking about? The little pluggable terminal box? AliExpress link in Discord. Yes. Cool. Thanks, Henrik. This is interesting. So, this is 2.54 millimeter pitch, which means that a 5-pin plug, let's see if we go to 5-pin, where is 5-pin? That's 4. That's 4. Anyway, I got all different sizes here. Let's find a 5. Nope, can't find a picture of a 5. Yeah, it'll still be quite long, but so you can do like orange for sensors, black for relays, and green for main board to board comms. DigiKey has heaps of those, says David Crisp. Oh, Mitchell said, yep, same thing. Okay, and you can get it in different colors. I like colors. All right, I had not really even thought about looking for small pluggable screw terminals, but that does seem like a good option. Now, the other thing to think about is what wire to use, and that would mean something like 5-core wire is kind of unusual. 6-core is easier to get. Don't know. Maybe something like no, I was just thinking like an RJ11 or RJ12 or something. Oh, and Henrik says, what about using RJ45? Yeah, but that ends up being too big. The sockets on the PCB for RJ45 are huge, much bigger than the connectors that I already have, and these connectors are too big. So I want to get something that is smaller than these 2x3s. Thin net cable. Jax Tech says, what is thin net cable? Let's thin net cable. 10/2. What? Ultra thin Ethernet cables. Ultra thin. What is thin net cable? Standard and thin net Ethernet. Thin net. Yeah. Coax. That's coax cable, isn't it? Okay. Oh, and Don said M8 industrial. Yeah, M8 connect plugs. This is getting into kind of expensive stuff though, and I use M8 connectors for CAN bus. I've done that a fair bit. That's what's on the wheelchair hand heater and on a few other things, because it's very rugged. With M8 connectors, they are designed for industrial applications, so they plug in and they have a screw lock on them. So you screw them on and they can seal really nicely. They've got so that you can't pull the cables out. M8 connectors, I really like them.
Said piece of string and 2 Ovaltine cans done.
Yeah, that's it. So I really like M8 connectors, but not for this application. They are, yeah, they're for like exposed external industrial connectors in a nasty environment where you don't mind paying a fair bit for the connectors and all of the trouble of terminations and things. This is just for an internal connector on a PCB inside an enclosure. This is for the cable that goes onto the PCB, and then the cable will come out of the enclosure and go to the sensor, which is mounted on the conveyor. Okay, so right, back to here. Is it here? Conveyor. Let's all right, on my to-do list, since it was pointed out, I am going to come on, info. I'm going to say check that patch has been applied. So that is on my to-do list. Now, oh, Henrik has sent me another cable link. Okay, let's see what Henrik is sending. Oh, okay, just different types of cables. Yep. This could be a, yeah.
Mitchell R said, nice part using the pluggable connectors. If you do 90-day, you can stick them out of the box, so it never has to be opened for standard maintenance.
Yeah, that's right. You can just plug and unplug. I agree. Are you looking for shielded cables? Why not use JST-SH? Yeah, I might end up just using JST. Like, what is the pitch of JST-SH? JST-SH, JST, what is that pitch? Come on. Size, SH, 1 millimeter? Does it say? Yes, 1 millimeter pitch connectors. Yeah, I might just do that. I might just use JST-SH. I've got JST-XH elsewhere on the board, like this one, I believe. That is, oh, maybe it's not. 102KF2510, that part number I think is like a Chinese equivalent of a JST XH connector, which is these ones here. Oh no, it's not, no. I'm misremembering. This is just like a keyed connector. That's a cheapy thing. But what did I put on this board? Oh yeah, this board does have, if we look at that, yeah, this board has these JST, I think these are JST SH connectors. Oops, and I want that. Yeah, so I could just use a JST connector on here. Oh, Henrik is still sending me links. All right, I am going to. So you asked, am I looking for shielded cables? I hadn't even considered it. I don't think shielded cables are necessary. Oh, this is cool. I've never seen these before. This is not really useful for this application because it's only 4-pin. But this is, yeah, extension cable for LED strip with like a pin header socket on each end so that you can link it in between your LED control, like between strips or whatever. That's quite interesting. And it's like a fully molded thing. Oh, they've got a 5-pin version. Maybe that was, oh, 5-pin RGBW. There is
Mitchell
a 5-pin
said
version.
Just do shielded. You never know where the squirrels will hide with odd behaviors.
Yeah, so Mitchell says I should do shielded cable. Yeah, this is kind of interesting. A 5-pin version of this, because it's, yeah, although, I don't know. Anyway, it comes in pre-made lengths. The length probably wouldn't be what I need. In fact, it would be more than I need. Even the short one, I don't need a meter length on that. And I'd have to pass the plug through a hole. So that's quite large and bulky. What I'd probably need to be able to do is run the cable through the frame and then attach the plug at the end. Trady says, solder it, do it right, do it once, I say. Yep. Okay. Oh, this is a... I was going to say this is off topic, but it's actually the only on-topic question for the entire stream.
Pluggable screw terminals win again, lol.
Yeah, I think Mitchell is right. I'm going to go for small pluggable screw terminals, most likely, or JST connectors. Don't know. So Pato asked, if you were to build a home from scratch, what would you use to automate hardware lights? I'm about to start building my house in like 4 months and starting to plan. Okay, if I was doing a wiring job for home automation right now and I wanted to be able to control it like DIY as much as possible, I would use Shelly Pro 4PMs in the switchboard with a star topology. So I would wire the lights back to the switchboard and put Shelly Pro 4PMs in the switchboard and use that to control each of the lights. It gives you lots of flexibility, and the topology is compatible with other high-end automation systems that use a centralized switching process rather than switching at the load. Yep. Henrik Holtberg said, Shelley, yes. Yeah. That right now, that would be without question the way I would do it. Yep. Oh, okay. Last one today, says Henrik. All right. This is another link that Henrik has just sent. And then I only have 15 minutes left.
System notification. 15 minutes remaining.
3 cores, 3 cores, 4 cores. There's no 6 cores, but we could go for, I mean, there's no 5 cores, but we could go for a 0.15, 0.2 millimeter, 0.5 millimeter. Let's see, go for that one in a 5 meter length. Ooh, that's expensive cable. But yeah, that is interesting cable. All right, now I wanted to get back to, Shelly 3EM. Is this a Shelly I haven't heard of before? Shelly 3EM. The Shelly keep coming out with new, it's a 3-phase thing. Okay, yeah, that's not what I would use in this application. So that's what you would use for monitoring power. If you were monitoring 3 phases, so lots of power going to a house, that would be cool. Switching, triggering. The one I would use is this one here. Although let's see, Shelly Pro 3, 4 p.m. dual cover. I'm just checking whether there are new ones that they've brought out. Where is, because there could well be others that I'm not aware of. What does the Shelly Pro 3 do? 3 outputs, 16 amps each. It's just a smaller version without the screen and without power monitoring.
Outside the box says that Mitchell R. have Mr. Beast queued now.
Yeah, this one. This, without doubt, would be my solution. So there is now one of these in the switchboard here at the Super Lab. An electrician installed it a couple of weeks ago, and it's being used for, it's linked to a couple of power circuits that go down to the back of the factory into Lachlan's area, including the new hot water service. So the reason it was put in is that Lachlan had a new hot water service put in. It's one of those heat pump type systems, and it needed a circuit run for it. So the electrician was here messing around, adding things, and he ended up installing a Shelly Pro 4 p.m. and we've got that running a couple of circuits now. So you can do control of individual loads and power monitoring of each of those loads. It's got Ethernet if you want to hardwire it. It's got Wi-Fi if you just want to use Wi-Fi. Yeah, it's all good. It's a, and it's got a little color screen on it. So no downsides to that one that I can see so far. Just going to close a few tabs here. JST, yes. So back in here, I'm going to say, as a reminder, once again to myself, replace, come on, replace sensor connectors. JST, what was it? XH.
Said Jono.
Or
next week is Christmas Eve. Are ya going to say hi here? Or are you off for a while?
No, I think I will be saying hi here. Or pluggable terminals. I'm just going to put that in there. So just to remind myself of what the options are, I've got to decide whether to go for something like a JST connector or a pluggable terminal. Okay, now, getting back to this whole thing that started all of this, which is what I thought I was going to be doing
whoop, whoop.
the entire stream about today, is CAN bus interface. CAN bus. So we've got the 2 CAN bus connectors here, and then our local CAN transceiver, which is linked to the bus. And it's just a pass-through bus. We are merely one node on the bus, and it has 2 connectors so that you can have cables going to the upstream and downstream devices. So from a coordination point of view, what this allows us to do...
Outside the box said cool, a Christmas presents from Jono.
Christmas presents from me. Yep. So I'll give you a dose of oxytocin as a Christmas present. So the rather than just the dry contact, so the ready in, ready out, like upstream, downstream connections, which can be useful for very crude signaling between machines, where devices only know about the adjacent machine. They don't know about anything else. This gives us way more capability. So by having a CAN bus connection, and
Imogen Ann said the wheels on the CAN bus.
yeah, the wheels on the CAN bus, do they go around? Then yes, it could be done with Ethernet. That was actually my original idea. I was thinking of putting Ethernet on this controller and then using MQTT or something like that for coordination. But you can also do that over Wi-Fi. This controller, because it's got an ESP32, can do Wi-Fi, which means that you can use MQTT for monitoring and control. But I thought that a CAN bus would be a good choice in an industrial, kind of semi-industrial environment. I mean, a pick and place production line is not super industrial. It's actually a really clean environment. It's electrically not too bad. There's the big oven at the end, which uses a bit of power, but we're not really talking about the sort of place where there's going to be arc welders and big motors and all that sort of electrical rubbish going on that necessitates a very durable communication system. But still, CAN bus is a reasonably cheap, in fact, compared to Ethernet, it is cheap. Like this, when you stop and think about it, it is actually amazingly capable for a very small amount of money. Because what we're looking at on the screen right here, this is all you need to enable CAN bus on an ESP32, because the ESP32 already has a CAN controller built into it. There are two critical elements when you want to link a microcontroller to a CAN bus. So if, for example, you wanted to link a microcontroller to an Ethernet network, you need an Ethernet controller and you need some kind of a PHY, like the physical interface that acts as the sort of the isolation between the logic level on your board and the big bad world of the Ethernet that you're plugging into. It's similar with CAN bus. So the ESP32 has a built-in CAN controller, and then all we need to do is have a couple of I/O pins. So in this case, I've got I/O4 and I/O5 as CAN TX and CAN RX going to a CAN transceiver chip. So on the left-hand side here, we have the logic level. So this is 3.3 volt level going to the ESP32. And on the outside, we have CAN high and CAN low. And that's it, apart from some optional things, like I've added a transient voltage suppressor here connected to the CAN lines. And there is the CAN termination, which you need to enable at both ends of the bus. But apart from that, we've got this CAN transceiver. So this CAN transceiver, this particular part number is a TCAN332DR. That's a...
Imogen Ann said random Steve Way. What programs do peeps use for 3D modeling to send to print? I've heard Blender isn't the best option because there is room for models to have invisible holes in them.
Okay, that can be a question for the audience. I'm going to stay on this for now. So the... what was I saying? That's right. Okay, so this is a 3.3 volt capable CAN transceiver. Now, CAN, which is a fudge, CAN transceivers really should run at 5 volts, but there are 3.3 volt capable transceivers that do some fudging internally with little internal charge pumps and stuff, because CAN is meant to be like a run off 5 volts, because I won't get into the details. I can talk about the internal details of CAN bus signaling sometime. It is really interesting. It is a differential signal that is zero referenced off a 2.5 volt
System notification,
yes.
5 minutes remaining.
Almost out of time. So a recessive bit, when the bus is not being asserted, it should float at 2.5 volts relative to the ground reference, and then the CAN high and CAN low drive in either direction from that 2.5 volts. So CAN high goes above 2.5 volts, CAN low goes below 2.5 volts by a volt each, I think. So it goes from 1.5, between 1.5 and 3.5 volts differential between the CAN high and CAN low, but you can't achieve the 3.5 volts on CAN high if your chip is running at 3.3 volts, unless it uses an internal charge pump to build that voltage up. Anyway, lots of stuff that I can talk about that, because I have spent so much time screwing around with the very low levels of CAN bus and failure modes and how the signals work on the wire. Yeah, I have a lot of painful experience with that. So I'm not going to get into that. The point is, you can add like a $2.50 IC, this CAN transceiver. There is also the one that I typically use. So this is the TCAN332DR, which I think is from Texas Instruments. I can't remember. Anyway, there is also the SN65HVD R231. That is the one that I most commonly use. I've got an entire reel of that on my pick and place machine because I do so much of it. So the SN65 HDVR 231 is also a 3.3 volt capable CAN transceiver, and it is like $2.50 in small quantities. So to add CAN bus capability to your project, all you need is a transceiver, a couple of optional things, and connectors, and that's it. So for a few bucks, you can have fairly high speed, like a megabit a second, extremely resilient networking added to your project to link these devices together. So in the end, in my head, I was kind of going over, do I put Ethernet on it? Do I put CAN bus on it? And my reasoning went, CAN bus is both cheaper and easier than Ethernet. It's more resilient in a noisy environment. And if I wanted to do things like MQTT, then I've already got Wi-Fi, so I can use it for that. Now, of course, I could do both Ethernet and CAN bus, but I only got so much time, only got so much board space. Yeah, and as Trady Trev said, and it's just 2 wires. It's 2 wires plus ground. You do need the ground reference. So technically it's a 3-wire bus, even though people say CAN is a 2-wire bus because it's just CAN high and CAN low. This is actually one of the misconceptions that a lot of people have. Because it is a differential bus, it's the voltage difference between CAN high and CAN low that matters. That's what signifies the zeros and the ones. And on a differential bus, normally you only care about 2 wires. It's just like the 2 signals. Hang on, I've got to go from right to left. So the 2 signals come in and then they deviate and then they come back together and then they deviate and come back together. And it is the delta between the 2 signals that gives you the zeros and the ones. But the thing is that CAN bus is not just the differential between those 2 signals, it's the differential between those signals relative to a ground reference. So you need 3 wires for a CAN bus connection, even though it is a 2-wire differential bus. But most of the time you've got a ground reference anyway, so that's cool. And what's really common, as you can see here, is to treat it as a 4-wire bus, because adding the 4th wire means that you are passing power and data down the wire. So you've got a megabit a second of connection in an extremely resilient way, with power as well.
System notification. Stream is over.
No, it's not. Okay, so CAN bus. Now, I've just been talking about some of the electrical aspects of CAN bus, but this is coming back to Sion's comments earlier about SMEMA and getting into a state where you don't necessarily know where things are in your chain of devices and what state things are up to, because what I want to do is use this CAN bus not just for checking state but also for sending control signals. For example, I want to be able to send a signal. Okay, here we go. Oh, Scott says TRR plugs are excellent for CAN. Yeah, that's true. Stephen says the bits on the CAN are still going around and round. Now, a piece of paper. All right, I'm going to try drawing a diagram. When I draw diagrams, I normally kind of have a picture in my head of what the diagram is going to look like. This time I do not. No, that's horrible. I'm going to get another piece of paper. And after I've drawn this diagram, I think I'm going to wrap up then, because it'll be about time to stop. Ooh. So, now, what am I going to diagram here? Okay, so this is kind of a combination of, what am I going to say? The physical layer and the software layer. Okay, so, say we've got, all right, I'm going to say I've got my KO PNP there, and say we're looking at this from, oh, it doesn't really matter. All right, looking at it from the top, say I've got another KO here, KO, and then internally, in between them, we've got the conveyor. In fact, I'm going to draw the conveyor lines through the KOs because this is kind of what matters at this point. And the conveyor has its little green.
Unexpected maker said, please. No drawing of the male reproduction organs moving face.
I'm not going to do that. I'll spare you, Sion. All right, so we've got the green anti-static or static dissipative or whatever they are conveyor belts. So we've got the pick and place machines and we've got the conveyor in the middle. Now, how am I going to draw this? Okay, connected to here is a PC running Open PNP, and that is connected to the Open KO board. That's USB, and then the Open KO board, I haven't allowed myself room here, is plugged in to control the KO to send it commands like home or adjust the conveyor or move nozzle 1 to position XY or, you know, turn on suck or blow or whatever. So the Open KO board is taking Open PNP's commands and telling it to do all of these things. And this is the serial. So it's an 8-byte binary serial protocol thingy. All right, this is getting really messy already. Now, this is what we currently have. We've got Open PNP. We have the Open KO board connecting by USB. So here we go, right here. USB from the PC comes in here, and then the output there is what goes to the KO. This is what sends it commands to move the conveyor. That's the thing that we care about right now, is moving the conveyor. So I'll put that aside. Now, what we're going to do is introduce the next element in the picture, which is the conveyor controller here. Now, this conveyor controller can move the rear rail, so it can adjust the width, and the KO can adjust its width as well. And it can run the conveyor, and it connects to the sensors. So it does all of the things within this part of the system in isolation to know how to move this.
System
But
notification.
coordinating
Peter
this
5 minutes ago.
is the issue. Now, I'm going to do a group. I'm not sure if I should introduce this complication at this point because I've actually have multiple KOs. I think it might be best to ignore it, but I'm just going to draw this part in here for completeness at the moment. So we've got a second pick and place machine here, also being controlled by OpenPNP, and it is doing its thing. So if you ignore the bit in the middle, essentially it's like two independent systems that can both do an assembly job. You feed a board in, puts parts on it, comes out the other end. This one can do the same thing. Now, how do we coordinate all of this? Now, this is where the SMEMA versus whatever, you know, it's the ready in, ready out. It's the connections at the interfaces here that matter. So, danger point right there, danger point right there. Now, this is where I was thinking of bringing CAN bus into it because OpenKO has the CAN controller on it. We have CAN on the conveyor controller. So what we can do is loop from OpenKO into the conveyor controller, and from here we can go whoop into the next one. So basically we're building ourselves a chain. We've got a CAN device, and the bus comes along here to another CAN device, and the bus comes along here to another CAN device. So we can pass messages between all of these devices over the CAN bus as very high speed, well, reasonably high speed messages in a very resilient way, with handling of collisions and all of that stuff taken care of. So that means instead of using ready in, ready out on here, but like the traditional connections between them, we can have our back channel communications coming over the network here. So first real benefit of that, in OpenPNP, in fact, I wonder if I can bring it up. One of the things that I can do in OpenPNP, no, I won't bring it up. Inside the interface, there is an actuator option. So I can click a button in OpenPNP and give it a size. Like say I know that this conveyor has to go to 142.3 millimeters of width to handle a panel that I want to put in. In OpenPNP, I can put in 142.3 as the conveyor size for this job, and that gets communicated to OpenKO. OpenKO sends the command to the KO, so ignore all of this for now, and the conveyor adjusts to 142.3 millimeters. That's all fully functional. That's working exactly the way I want it to right now. That's all good. Now this is where the next step comes in. We're already sending the command from OpenPNP saying go to 142.3 millimeters. It goes in through the OpenKO board, which then sends that command out to the KO, which adjusts its conveyor. Brilliant. Next step is we want this conveyor to also move to 142.3 millimeters. So this is where the firmware changes come in. So what I was thinking of doing is in here, in the firmware, is that still on the page? Just. Firmware, I want to route the messages both to the KO and to CAN bus. So when we send a command saying to go to 142.3 millimeters, it sends the command to the KO, which responds, and also broadcast on the bus that our desired conveyor size is 142.3 millimeters. And that would be picked up by devices on the bus, which could then act on it. So what we could do is send it from OpenPNP running on this machine here, send the command that we want to go to this width, The local KO gets it through the serial connection, and then it passes it to the bus. The conveyor also gets it because it sees a message on the CAN bus, and it then adjusts itself to 142.3 millimeters. And also on the CAN bus is this other open KO board running on the second KO, and that also then sends a command because it receives the CAN bus message coming in saying to go to that width. It then sends the serial command to the KO, which adjusts its width. So what I want to be able to do is click the dialog in OpenPNP here, put in a number, and have all of the machines in the line automatically adjust so they all go to the same size. And yeah, be nicely coordinated. And that I think we can achieve really easily by using CAN bus. And that is why this has a CAN transceiver on it right there to receive the incoming messages and potentially send messages. So we could send back status messages like whether there is a PCB detected on the conveyor. So this board here is right here. That is what's managing the conveyor. This board is right here. That's what's managing the KO. This board is right here. That's what's managing the conveyor. So CAN bus coming out of here goes to here, and CAN bus coming out of here goes to the next open KO board in the chain, which is here. Now on this particular one, I've only got one CAN bus connection on this open KO board, and ideally there should be two, because we want to be able to have a series of these in the bus. But the nice thing about CAN bus is that you're not interspersed in, like, how do I say this? You're not interrupting the connection. If we draw the topology of multiple CAN devices on a bus with CAN high and CAN low, like this, and there's a ground reference of course, this signal here, this CAN high signal, is actually electrically connected to this. There is nothing in the middle here that is blocking the signal. So it's more accurate to draw it like this. It is multiple devices, and then we've got CAN high connected to all of them, and CAN low connected to all of them. And these devices just connect into the same pair of wires. It's electrically the same all the way along the bus. There's no interruption to it, which means that if we have a device like this, which has just a single CAN bus connector, all we need to do is wire the two cables into it. So the plug that goes into this, like this, can just have the two parts of the cable wired in, and we can have a connection in that direction and a connection in that direction, plugs into the board, and everybody's happy. Having two connectors like this, so electrically these are on the board, these are directly connected. If you buzz out this with a continuity meter, that connects to that. It's just because it's rotated 180 degrees. That connects to that, that connects to that, etc. So it's just a direct pass-through connection. The only reason for having two connectors is convenience. It's just so you can plug in a cable there, plug in a cable there, and not have to worry about wiring two cables into the back of the same plug. But we can achieve the same result just by wiring two cables into that plug and plugging it in. So then we end up with, coming back to here, back to the cunning plan, back there. Okay, then we end up with, in this scenario, 3 controllers on CAN bus that can all be accepting commands from OpenPNP. Now the interesting thing is, depending on how all of this software is set up, of course, we could run OpenPNP on this machine and send a command to set the conveyor width, and all 3 machines would respond, including this one. Or we could open a dialog on this one, send a command to set the conveyor width, and all 3 machines would respond. So you could actually drive the line from multiple instances of OpenPNP. And yes, I know that potentially leads to concurrency things, like this machine thinks it's at a certain width and this machine thinks it's at a different width. But that doesn't actually matter for various reasons.
System notification. Peter is super hungry.
Okay.
15 minutes ago.
All right. Hang on. Where am I? Where is the chat? Let's get back here and what have I missed? What have I missed? I'm scrolling back. I am going to wrap this up now because it is now 12:15. Oh yeah, that's right. Back to here. So Scott had said TRR plugs are excellent for CAN. Wagon Load says on CAN bus, do the high and low always change at the same time? And the answer is yes. And and Stephen says differential signals always move at the same time to help reject noise. Scott says, wonder how much time John spends trying to clean up the Sharpie bleed through from his desk. How much is there? Oh, not very much. Almost none on the desk itself. Trady says, this is like I'm working at the factory all over again. Do the same thing using... Wagon Loads suggest using MIDI. Yeah, well, MIDI is just based on RS, like it's a multi-drop RS485 or something, isn't it? It's like a protocol on top of RS485. So Wagon Loads 2 asked a question, can PNP2 tell PNP1, I'm busy, stop sending new PCBs? Yes, that is exactly what this whole thing is meant to be about. It's about queuing, because you can end up with a stack of PCBs working its way down the queue, and unless every machine finishes faster than the one before it, you are always going to end up with a queuing problem where, say your first machine...
Magic eraser will get the Sharpie bleed through off your desk.
Cool. So the say your first pick and place machine takes 1 minute and 12 seconds to populate a board, and your second pick and place machine...
Lawler said Steve and Steph proof of life.
And your second... Oh, they're actually not here. They're out because I had them out for the barbecue. The second pick and place machine takes, say, 1 minute and 30 seconds to run its part of the job. Then the first machine is always going to have to know that the next machine down the chain is not yet ready. That's what the ready in-out signals are for in the basic signaling method. So the upstream machine will sit there and wait. It'll get to the point where it has a board ready to send to the next machine. It will check the interface on the next machine and say, are you ready for a board? Are you ready for a board? And if it's no, then it just sits there and wait. So you then end up with a stack up situation where each machine ends up waiting for the one downstream from it. And if you have a bottleneck at the end, then you end up with boards stacked up the process, each one waiting to move to the next stage in the process. And the process only moves as fast as the slowest machine, or the longest cycle time, I should say, at each of the stages. And then when the downstream machine, so PNP2, has finished its board and moved it on, like to the oven or whatever, wherever it's going, its interface then says, yes, I am ready to accept a new board, and the next machine, the machine up the line, sends it along. So, Peter says, I'm going to report you to Vic Pol for rodent murder. They're not here. What do you think I have done with them? No, Steve and Steph are quite happy. They're out in the factory hanging out with the possums, with their friends. Nick Wagon said, I went with RJ45s for bus connections. So much easier. Yeah, RJ45s they are a convenient connector and convenient cabling. Steve the Squirrel said to Peter, happy birthday to you, happy birthday to you. Here is a nut drink to your big day. Happy birthday, Peter. Oh, people's minds are going into bad places. David said hanging with the possums. I have not hung Steve and Steph. They are perfectly healthy, happy and hale. They are They are just out on the bench where we were having the barbecue last weekend. Oh. So, what am I doing? I don't know. Anyway, my point. So, what I was actually going to do today. Proof. All right. I will get proof. So, this is what I was going to do today. So this is the firmware for the OpenKO board. We've already seen this because we've been looking at OpenKO for a while. It's got the, these are the buffers for the 8-byte binary protocol that the KO speaks. And yeah, it's got tracking for the X and Y position, like where the machine currently is, and angles on the nozzles and things. So it's got arrays to track the 4 nozzles. Etc. So currently what it does is accept G-code from OpenPNP, and then it sends, like, so you could say G0X123 will move it to 123 millimeters on the x-axis, and one of the commands is, here we go. There's run conveyor, stop pin engage conveyor, clip PCB, exit PCB, ingest PCB, etc. So these are all of the conveyor related methods. And let's see what happens. For example, where is it? Adjust conveyor width. Where is adjust conveyor width? And because this is the crappiest IDE in the world, I have to do that to find it. Find. Oh, come on. Adjust conveyor width. There we go. Okay. So when we call adjust conveyor width and we tell it how wide we want it to be, it checks first if there is a a size. It creates the message template for the conveyor width adjustment. Does some dodginess in here to do the calibration. So the KO uses 0.1 millimeter units for conveyor size, and then we have to format that correctly and add an offset, which is based on the homing correction value. I'm not going to get into this in detail, doesn't matter. And then it sets the it forms the message and sends it to the KO. So this point right here, this is the critical thing. We are sending the message to the KO of the conveyor width. So what I had in mind was something like send message to CAN and we'll give it width requested. Something like this. Now this method doesn't exist yet, but this is what I had been thinking of doing, something like this. And then what I'm going to need to do is add a, let's do new tab. Oh, what am I doing? I'm actually comms.h, that'll do. So we've made a, we've made ourselves a thing, and then let's do that, and then and if each can comms. So we're stubbing ourselves out of a file to put all of this in, and then up here, where? Here we go, machine actions. Oh, we've got serial comms. We can do include can comms.h. It's one of those things where doing it is almost easier than explaining it. All right, so then in here we would stub out, where is it, machine actions. I would stub out something that does this. So let's say, for now I'm just going to make it void, but of course we would want to have it return a success or fail or something. Nothing. Yeah, so what do we want? That'll be a float. And just for the hell of it, we could do serial.print.
Cable Pi said use Copilot to write send message to CAN for you.
Maybe. Yeah, I wonder if it probably does understand J1939 messaging. I don't know. I'll check. Serial print, sending CAN
Peter Lawler
for...
said this is some rather extensive diversion from Steve and Steph proof of life.
I'd hoped you'd forgotten about that and you wouldn't discover that I am a serial killer. Serial print line width requested. Okay, so this is going to do nothing much useful now. It's simply going to... In fact, let's see if this compiles. OpenKO, do I have the S3 selected? It probably is. Am I compiling it for an S3? I don't know. It'll bail out if it's not. It'll freak out. So at least now we've got a stub. So we've got machine actions. When we send a command to the KO to go to a particular conveyor width, it is now going to call the send message to CAN with requested. No, this is wrong. This is bad, bad, bad. What I should do is call this something like send conveyor width to CAN, because it's not just sending a message. It's not a generic thing. It is send conveyor width to CAN. That's better. So because they're going to need to be like a generic. There will be other messages in here. There's going to be a lot of code in here.
Cries out dramatically, my cornflakes, loudly crying.
What?
Peter Lawler said call it send
My
Steve to the
cornflakes.
mortuary.
Okay. Okay, I am going to go and hang on, I thought I heard a car out the front here. Oh, it's someone over the road grabbing firewood from Stewart's sawmill. All right, just so that nobody reports me to the Royal Society for cruelty to squirrels, here we go. Steve and Steph, proof of life. There they go. Oh look, there's Steve, there's Steph.
Imogen Ann said serial killer.
Serial killer. Yeah. Yes. So this thing.
Peter Lawler said CGI is getting very good these days. In it.
You don't. They look stuffed to me. Yeah, it is just their stuffed carcasses now. Yeah. I mean, if Steve was really alive, would I be able to do this? No. So anyway, the point is,
Some call it
I
fun,
need
says
to-
you. You've had them taxidermized.
I have indeed. They are stuffed. Just stuffed squirrels. Now, this is just a very basic stub, obviously. It doesn't do anything useful. We don't have any CAN communications established. We don't have the driver for the CAN loaded. We're not sending an actual message. We haven't defined a message format. But this is just to explain to you what I have in mind as the process. This is where I want to go. Scott says I should. Scott and Stephen both said I should wash that finger. So where am I? That's right. But all of that sort of stuff can come. That's all the supporting things that go around this.
Peter Lawler said, now I'm really reporting to you, the Squirrel Protection Society.
Yep. Yeah. But this at least shows the concept. I think this
Imogen Ann
explanation...
said we have all devolved and are in the gutter rolling on the floor laughing.
We have. So, in summary, this is what I want to do. Message from OpenPNP comes into OpenKO. OpenKO controls its own directly connected KO. I mean, I could make a multi-channel OpenKO board that controls multiple machines, but I don't think that actually makes a whole lot of sense. It also sends that same message out on CAN bus, and then all of the other devices on the same bus also adjust their conveyors to match whatever we have requested. So one copy of OpenPNP here can change the entire production line.
System notification. Stream is over GHAAA.
Yeah, go. And by doing that in here, so I've already got all the machine actions in here, like adjusting conveyor width, and I've got load and unload conveyor. Like if we come back into, where was it? Here we go. These are all the conveyor related methods in the OpenKO firmware. We can run the conveyor, we can stop it, we can reset it, adjust the width. Resetting it is homing. We can engage the stop pin, which is what makes the PCB stop at a specific location. We can engage the clip that latches the PCB in place. We can bring a board in, we can send a board out. So all of those useful things. So what we can do is then have coordination between the different devices where we know, for example, whether the conveyor that is downstream from us is ready to accept a PCB, and then we can run exit PCB from the conveyor. And conversely, if we are a machine that has an upstream, so there's another conveyor that wants to send a board onto us, we can communicate with that, decide that there is a board, yes, it is going to run, and then we can run ingest PCB on the conveyor. So all of these methods are already in OpenKO. Like we can already do this. We can load boards, we can send boards out, we can stop them and latch them and all of that sort of thing. It's the coordination of this overall system is the next thing to do. And that is where this comes in. So, yeah, there will obviously need to be methods in here. We're going to need to do things like, we're going to need to define a message structure. And that message structure is going to include things like a message for setting a conveyor width. It'll also be things like querying whether a particular device is ready to accept something and responding, saying whether it is or isn't, etc. All of that stuff. But we can define all of that once the basic CAN communications is up and running. Right. Okay. I am going to stop. I'm going to stop. Seriously, I am going to stop. Right. What do I need to apologize for? Henrik said, first time Steve is mad, you need to apologize. Yes.
John.
Yes, I'm sorry, Steve. Okay. And Peter wants me to go home. Okay. So, thank you for coming. And this week was a lot of talking and no actual doing anything. But, oh, that was my shoulder just went crunch. You probably heard it. Henrik says, John has no home. His home is the lab. That's exactly right. I am homeless. Oh well. Okay. I am going to go... Sion said, cheers everyone, yes, my fault. No, you brought up excellent points, and your experience with this is, and sharing your experience with this is very much appreciated. So thank you, Sion.
Said BYE.
Stop. Okay, I'm going to go. I hope you all have a fantastic week. 1 week until Christmas. Next live stream is Christmas Eve morning, and maybe by then I'll actually be doing some CAN stuff. I would love to have an OpenKO board and a conveyor board here sitting on the bench, connected by CAN bus, and be sending messages between them. I think we can do that next week. That'll be cool. All right. Time for me to take a breath, and for you to all say, thank God he's stopping now. Okay, have a good week. Go and build something awesome.